Heating curves. This is a heating curve showing how temperature changes as we add heat. In this case, this is for 1 mole of water. So down here, obviously we see negative Celsius, so we're starting with ice down here. And when we have a single phase of a substance and we add or remove heat to it, the temperature changes in response. So if we add heat, the temperature increases. The relationship to temperature and heat is given by these equations, where Q is heat is equal to specific heat times mass times change in temperature. Specific heat is unique for the substance along with its phase. Specific heat is based on the amount of mass or grams of a material, which is why we have mass in the equation. The other form that we can see is using the molar heat capacity, where it's based on the amount of moles of material, in which case we're multiplying by moles in that equation. So by seeing the heat capacity units, we can tell whether we're multiplying by mass or moles. Heat capacity here will be joules per gram degree C, or Kelvin. This would be joules per mole Kelvin. So when we're adding heat to a single phase, the temperature will raise. This will tell us at what rate it will raise. But then when we start to change phase, we'll end up with two phases. And when we add or remove heat when we have two phases, we're not going to change the temperature, but we're just going to change the ratio of the phases. So we're going to freeze or melt, evaporate or condense. So that's represented by the horizontal lines on this graph here. The lower one is the melting of ice, and the higher one is the evaporation of water. The relationship is shown by here. We have the heat is equal to moles times the enthalpy of transition. So if we're talking melting, it would be the enthalpy of fusion for melting, and that's whether we're melting or freezing. And if we're evaporating or condensing, it will be the enthalpy of vaporization. Sometimes you might see the enthalpy on a per gram basis. If it's on a per gram basis, we multiply it by mass. If it's on a per mole basis, we multiply it by moles. So when we have two phases, we're just going to be evaporating, condensing, or melting, freezing. When we go over a range, we might go over a couple different portions. So this one shows a pretty complete set of the three, shows a complete set of the three standard phases: solid, liquid, gas. So if we have ice, we add heat, it raises in temperature. When it hits 0 degrees, then it melts. Then when we only have water, the temperature raises till we hit 100 degrees. And then we keep adding, and we're evaporating the water. After we evaporate all the water, then we can raise the temperature of the steam. If we want to calculate the heat required over a range of this, we pick the equations that we need. To do the full range here, we're going to use the specific heat equation 3 times on all the slope portions of the graph. Each time it will have a different value for the specific heat. Then when we melt and when we vaporize, we'll be using this equation, and each time we have a different enthalpy of transition. So enthalpy of vaporization is different from enthalpy of fusion. The heat of the whole process is a sum of the heat of different steps. So we will use the specific heat to warm ice, heat of fusion to melt ice, specific heat to warm water, heat of vaporization to evaporate the water, and specific heat of steam for the final step.